This is Mr. McMurray, and we're here studying Newton's third law today. And we're going to start outside, do a couple examples, and then we will head back inside for less exciting things. All right. First of all, we're going to start with a bottle with just a little bit of Bridgeport's finest water poured in there. Not a lot. Don't want it to be real heavy. All right. We have a little bit of that. Okay. Now I'm going to put this. I have a stand over here, and has a cork on it. And we're going to put that cork on there. We're going to clamp down, clamp over that, hold it on there. All right, so just like you said, this is the stand, goes in the ground. We have a cork that's in here. We have a hose coming out that we're going to pump air in here and build up pressure. That's going to supply to our force that we need for this experiment. All right, and we have a bottle, of course, with the water on top of that. All right. So, all right. Now I'm going to attach the air pump to that and pump it up. Okay, that's going to increase the air pressure in there. There's nowhere else to go. All right, we'll see how much pressure we got. I don't know, it's hard to tell. It's not fitting really good, but we're going to try it anyhow. All right, pulling this off. And there we have our launch. It landed back over there. A little messier for the wear, but that's okay. All right, and that was our first one, our air bottle launch. All right, this is Mr. McMurray in the shade this time. Hopefully, it'll be a little cooler. But anyhow, we have another bottle, different bottle, but same difference basically. All right, and this time we have a suspicious white powder. No, not really. It's actually baking soda. Fairly simple stuff. Feel free to do this at home if you like. Just be safe. All right. And I have a silver foil boat of sorts. It's going to hold as much of this baking soda as I can get on there. All right, I'll get that loaded up, and then we'll come talk to you some more. Okay, this is Mr. McMurray. We have now put our little boat full of baking powder inside our bottle. Not nearly as hard as getting a, say a boat inside a bottle, but hey, I'm a beginner. Maybe I'll work my way up to that. All right. Now, we are going to put some pencils on the table. Hope they don't blow off here. Okay. And as you can probably guess, that's to reduce the amount of friction. Okay. Now, we're going to put some vinegar. And we all know what happens when you put vinegar in with baking soda. It begins to bubble, right? It makes volcanoes. So what we're going to do is do that. And then we're going to see what happens after I put a cork in it and mix it together. Up there. Mix it up some more. Let's see. Did you hate that? Okay. All right. It did shoot off. Theoretically, had it been here, this would have shot off this way a little bit. About hitting 50% for our demonstrations today, okay? But normally, if you put that on there, it will shoot off the cork that way, which it did quite a bit ways, and it shot the bottle a little bit. I was holding it. It probably would have got to the end of the table here, but probably not falling off. All right. So, someone said, what does all that prove? Well, let's talk about it when we get upstairs. Experimenting. A little bit of blood on me, but we're okay. Other than that, we're good. That's good. No, it was just mud, but not blood or anything. All right, we're back indoors now. And a couple things. First of all, I want to hit a few highlights from chapter two. Usually, chapter two or three, Newton's second law, sorry, usually gives people a little bit of trouble. All right, a couple things. One, if an object is in free fall, which means only gravity is acting on it, it will accelerate at 10 meters per second. 10 after 1 second, 20, so forth. And it will continue doing that forever if the only force acting on it is gravity. Okay, or when we drop the golf ball and ping pong ball and the darts, they hit it at the same time. Why? Because there is air resistance, there was air, but it was the difference between the air resistance of one and the other, because they're about the same size, it was negligible. Not negligee, guys, don't be picturing me in a negligee. All right, it is negligible, which means there's not enough difference in their air resistance to do it. So they will fall at the same rate if there is a negligible amount of air resistance. However, we know most things have air resistance, and therefore they don't fall at the same rate. And that's where terminal velocity came in. It will begin to accelerate, but as it moves faster and faster, the air resistance will get greater and greater, and eventually the air resistance will equal negative 10 meters per second squared, whereas the gravity is pushing it 10 meters per second squared down. And at that point, you have the net force of 0, which means not that it stops, but that it goes at a constant speed and quits speeding up. Okay, a lot of people were saying that's due to gravity, but if it's just gravity, it would just keep speeding up more and more and more. Okay, all right. The other thing is when we throw a ball up in the air, it is constantly accelerating. It's slowing down on the way up, but that's deceleration or negative acceleration, but it's still acceleration. It's a change in velocity. If it goes faster or slower, either one, that's acceleration, okay, in physics. Also, if it changes direction. So as it goes up toward the top, right before it hits the top, it's still going forward, then it stops, and then it comes right back down. But it's just instantaneous. It doesn't stop and hang there for a couple seconds. It's constantly changing its velocity. 1 minute it's going up, and it still has a positive velocity. Then it's 0, and then it's negative as it comes back down, or positive, depending on how you want to look at that. So it's negative going up, and positive is speeding up, coming back down. But at all points of the path of the ball going up and down, it is changing either speed, direction, or both, and therefore it is constantly accelerating. Okay, now some people did say that if it fell far enough, if I could throw it high enough and it fell far enough, it might reach its terminal velocity, in which case, yes, it would no longer accelerate at that point. But if I just throw it up in the air, I gave you that because you're correct and you were thinking, and that's what we want you to do. All right, so let's get on to Newton's third law, which we're probably a little more familiar with, and it's not quite as complicated as some of the other ones. Okay. Basically, Newton's third law says all forces come in pairs. You can't touch something without being touched by it. Okay? If I have a hammer, hang on just a second. So if I had a hammer, sounds like a good song. If I had a hammer, I'd hammer in the morning. Okay, yeah, probably before your time. Look it up on YouTube. It's out there. Okay, so say I have a hammer, all right, and I'm going to hit this nail, all right. Well, obviously, I'm hitting the nail. But what we sometimes forget is the nail is also hitting the hammer, okay? Every time two objects touch, one exerts a force on the hammer, exerts a force on the nail. That's what we normally think about. But the nail also exerts a force on the handle. Same way if you hit somebody, you exert a force on their face, but they also exert a force on your hand. And that is why boxers wear gloves, to protect themselves, because they're getting as much force directed back on them as that. So Newton was very astute, and one of the things he came up with, the idea is that these were in pairs, okay? And he said this action-reaction, we usually call it. For every action exerted, there is an equal and opposite reaction. Now, when I hit the hammer on the nail, which one's the action force? Well, we would say, oh, the hammer hits the nail, and the nail hits it back, so that's the reaction force. So the hammer hitting the nail is the action. It doesn't really matter. It's kind of like which direction is north or south, okay? We call one direction north, the other direction south, but it could just as well be the other way around, okay? We just picked one direction and said that's the way it is, okay? When you have these two forces, they're identical and they're equal to each other, so it doesn't really matter, but one of them is the action force, the other one is the reaction force, okay? And so anytime there is a action force, there's equal opposite reaction force. Now, this is very important principle between many very valuable contribution societies that has made to society. Some of the most important ones, for example, is Newton's cradle right here. Whoops, let me move that a little closer. I'm sure you've all seen one, but we'll do it again. Say I take this ball right here and I drop it, and it hits the other one off on the other end, and it just keeps doing that. Okay, if I take two balls, then it knocks two balls off, and you get the idea. All right. And so it keeps doing that. Now, why does that happen? Well, it has to do with Newton's force. When this ball is coming down here, it exerts a force on this ball. But this ball also exerts a force back on this, and it's equal. So just as hard as it's hitting that ball, this ball is hitting back, which makes this one have a net force of 0, and so it stops. Okay, it cancels out the force, and so it stops. This keeps happening all the way across until it hits this one, where that cancels the force on the next to last ball, but the last ball comes flying off, and then it comes back, hits it with an equal and opposite force, and it stops it, and it passes that along, boom, 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 till it gets to this end, and it keeps doing that back and forth, okay? Now, besides that, there are some very important toys, sometimes called the most dangerous toys ever given to kids, and that's hard to say because there's been a lot of dangerous toys that have been made for kids over the years, but we call these clappers, okay? These are the ones that come in plastic balls. These are in good shape. They haven't cracked yet. Nothing like banging two hard plastic balls together until they shatter and send pieces flying flying all over the place. Okay, so I made a 2022 more version ready, and we use golf balls. Okay, but same thing. All right, as these balls hit, they hit with equal and opposite. Ooh, until I hit that. Okay, and they go back and forth. And so what they're doing is they're hitting an equal opposite. Boom, they're not just boom, and they stop their motion because they're equal opposite forces, and they just keep going back and forth, back and forth. Now, the more friendly safety version of that is this one. So let's see if I can do this. Some days you got it, some days you don't. You know. And maybe this is one of those days I don't. Let's see. Okay. The golf ball is usually the harder one, so we'll see. One more try. Let's do it. Oh, I got one or two hits. But anyhow, you can see it's not as more safe, I guess. The other thing, of course, is these kind of clackers, which just have a ball with a triangle coming to it, and on this side also. And if you drop them at the same time, whoops, they go back and forth, just like the other one. Now, the other option, which I have a harder time to doing, I'll be honest with you. All right, you can have this one come and it hits that one, but since they're equal forces, it stops that one, makes this one go around, boom, it hits that one, and then it comes around and hits that one. Okay, we don't have time. Well, there we kind of got it going. I don't know if you can see that, how good my recording here is, but at any rate, basically it does the same thing. It has to do with opposite and equal action forces and reaction forces, okay? And because of that, they're always equal to each other, okay? And so any force that exerts itself has to have those two. Now, for example, what's keeping me on the ground right now? Gravity, okay? So gravity is exerting a force on me, but we just learned that for every action force, there has to be an equal opposite reaction force. What's the reaction force? So, oh, the floor pushing up on me. No. Okay, now gravity does push me on the floor, and the floor pushes back. So that is an action-reaction pair. But the pull of gravity doesn't have anything to do with the floor. Okay, even if there wasn't a floor here, there would still be a force of gravity pulling down on me. So I jump off the roof. All right, so the reaction force is me pulling the earth up. Okay, now we'll talk more about this later, but because the earth is so massive, the result of that force is not very much, okay, because the earth is so big, that force that I exert on it, even though it's equal to the force that the earth exerts on me, it doesn't impress the earth much, although it will make me accelerate off the roof and kill myself on the ground, okay? So I won't demonstrate that. You'll just have to take my word for it, okay? Let's see. Action, reaction force. Now, one of the key things with an action, reaction force is that they cannot be acting on the same object, okay? A lot of times people get this confused, all right? My bowling ball and demonstrate. Why bowling ball? Why? Okay, here we go. So I've got my bowling ball, all right? Now let's just go ahead and put this down on the ground so you can see the bowling ball. All right, there we go. Okay, if I come up and I exert a force on the bowling ball and I kick it, and someone else kicks it from the other direction. Let's just say one person kicks from this side and someone pushes it from that side, okay? I can't do that without doing the splits. Okay, but question is that an action-reaction force? Say we kick equally hard, all right? So I've got a force this way and a force that way. No, that is a net force, okay? There's a force acting on the bowling ball, one of them focusing this way, one of them kicking this way. And if the net force is 0, it will stay here. Okay, but the action-reaction forces, it is action-reaction forces. It's actually 4 of them, okay? Because this one, my foot kicks the bowling ball, but the bowling ball also exerts equal force back on my toe. So if I just have thin cleats, guess what? My toe may be broken now because the harder I hit this, it's going to hit equal force right back to my foot. Same thing on this side. The action-reaction force is me kicking the ball and the ball exerting a force on me. When these two forces are both acting on the bowling ball, so they're acting on the same thing, that's not action-reaction. That's a net force, okay? And then depending if one's stronger, then it's going to go that direction. If the other one's stronger, it's going to go this direction. If they're the same, it's just going to sit there with the net force of 0, no acceleration. If it was just sitting there before, it's just going to keep sitting there. Okay, so keep that in mind. All right. They have to act on different things. So I kick the ball hits my foot, or in this case, my hand. But anyway, you get the idea. All right. I'm acting on the ball's acting on my hand. They're acting on different things. Now, since they're equal and opposite, sometimes they're going to cancel each other out. No, if I kick this one, that action is going to cause it to roll off this way. It's also going to make my hand bounce back and also hurt really bad. Okay, so it will not necessarily cancel each other out because they're on different objects. Okay, however, they can be the same. For example, oh, well, I forgot. That's okay. All right, here we go. So we're going to try this one real quick. If Mr. McMurray has enough hot air. Okay, I've got a balloon. Aren't you jealous? All right, and if I take it over here, I have a straw that's on this string here. All right, and if I let go of the string, or the balloon on the string, what's going to happen? It's going to shoot down the string. Why? Basically, Newton's action-reaction. There's air inside the balloon shrinks and pushes it out, that it's off the end, and the air pushes the balloon forward and carrying the straw and so forth down the string. Okay, and so that is Newton's that's Newton's third law, action-reaction. This is basically the same law that makes jets work. It makes rockets work. Shoot out the exhaust shoots out one end, and it is forced out, and it forces the rocket forward. Okay, I think we said in the lecture, some of the first people said, though, you won't be able to go to the moon because there's nothing for the rocket to push off of. Well, that's the point, is the exhaust, the fuel burning in it, just like the air inside the balloon, push against the rocket, and the rocket pushes it back out. It doesn't need any atmosphere or anything like that to go somewhere. All right, so let's try this one real quick. I don't know how well you can see this. I have a rope and I have a spring scale on it. Remember, this is a tension force, so I'm pulling on the rope. Okay, if I pull on this, I found my spring scale, by the way, and it shows that I'm exerting a force of, let's do newtons, of 20 newtons. Okay, so I'm exerting a force of 20 newtons on this rope. Okay, now if I got on the other end of it, I had another spring scale over there measuring the strength of my pull, guess what it would read? 20 newtons. Why? Because the force that I exert on the rope exerts on the spring scale. Okay, that means there's a net force pulling on this one of 20 newtons. At the other end, it's also going to pull 20 newtons on that faucet I hooked it around, and it's also pushing back against that. Okay, anytime you have a rope and you're pulling on it with tension forces, the force has to be the same on both sides. Okay, so for example, if I had, say I tied this to this and I had another person pulling with 20 newtons over here, guess what the force on this rope over here would be? It would still be 20 newtons. Why? Because the same amount of force is going to be the same. Because on this end, it's equal opposites. So if we have a force of 20 newtons, it's going to pull on me with 20 newtons, and that's going to pull me for this one with a force of 20 newtons. Okay? If someone's pulling on that side, it's still going to have a force of 20 newtons throughout the rope. Okay? And one of the questions someone asked me, how can anyone win tug of war? Okay? They also use the book example about the horse and the wagon, but I think that's in the lecture, so I won't go over that. If you're playing tug of war, the tension on the rope, it's not how hard you pull the rope, because there's only so much tension on the rope. It's going to be the same on both ends, all right, no matter what. Okay? But what is not equal, okay, so they're pulling this rope, they're pulling the rope, the tension on the rope has to be the same on both sides. It's not that someone's pulling harder on the rope. What's happening is really down the ground. Okay, on each side you have people who are pulling on the ground. Their feet are pushing against the ground. They're pushing that way. we know there must be an opposite force on the ground pushing this way. Okay, and so when I pull and push with my feet, okay, I'm pushing down the earth, but the earth's also pushing back against me. And that force, if I can push against the ground harder than the people on the other side, gives me a net force in my direction. So it's not so much people think, oh, we need someone with strong arms to help us win the tug of war. No, we need people who can push on the ground harder, so the ground will push harder against us and give us a net force over the people on the other side. They're pulling the rope with the same tension on it, but they're pushing against the ground, and the ground's pushing back them. So if we can push against the ground harder and make it push back against us than they can over there, then we will win the tug of war. All right. So really, if you want to win a tug of war, we could load all the guys on one side, girls on the other side. I can make the girls win. Why? Put all the guys in their socks on a slip surface, and guess what? They're going to lose. Why? Because they can't put pressure against the ground. No matter how strong their arms are or whatever, they're not going to win the tug of war. Okay. So it's really all about having good traction, cleats or whatever. And yes, you have to be able to push a certain hardness, because you still got to, if you can push harder against the ground than they can. But traction is probably just as important as the actual how hard you push on the ground, not how hard you pull the rope. Okay? That kind of goes against what we think is happening in tug of war, but welcome to physics. That's the way people think they know what's happening, and a lot of times it's not as easy as we think it is. And we teach a lot of things, especially in the lower grades, a lot of times that aren't true exactly. All right, let's look at some other examples. Another thing we're going to talk about here real quickly, we have a CD here. Yeah, that's back. I know it's hard. Again, ancient DVD CDs, whatever. Okay, and we have a soap dispenser lid, and we have some modeling clay holding it on there. Okay, if I open this, let's air through, and I'm going to blow up a balloon. We're going to have lots of balloons today. Fortunately, I'm full of hot air, so that is not a problem. We can handle this. All right. Now, if I take this and I open this, the balloon's going to do what? It's going to contract, which pushes the air out, so it puts a force on the air, but the air also puts a force on the balloon, which kind of lifts it up. Also, the air pushes on the table pushes back up against the air, and so both of those are going to give it a lift force. And so instead of just going like that, where it doesn't do anything, it's going to go and it's going to bounce back and forth, and you could play air hockey, except you got to go score pretty fast, because once it runs out of air, then it's not going to do it anymore. Okay, so that's once again opposite force. Now, helicopters, for example, when they fly, they push air down. That pushes up on the blades of the helicopter, which allow it to lift. Okay, birds, when they flap, they push down on the air, but the air pushes up on them. Also, as the air gets pushed up, it kind of swirls around and gives a little bit of lift to the people off to the sides here as they come through that air. And that is why you see geese in a V shape, okay? They figured out the physics a long time ago. Well, they didn't actually figure out the physics, but they've taken advantage of the fact, because that swirling uplift of air that's being pushed up when the bird brings its wings up, that push up of the air is going to also help them and give them some lift. So the ones following but off to the side get a little assist, if you will. And that's why eventually the lead guy will go back and get on the side and say, hey, someone else take the lead. And he also cuts that down the air resistance a little bit. But there you go. All right. Now, on to the next thing. Let's say, who can hit this paper the hardest? You, me, Mike Tyson, if he still boxes? I don't know. I don't know if the new people. So anyhow, the answer is, we can all hit it equally hard. I can hit as hard as the heavyweight champion of the world can, and it's very simple. Because if the action force is equal to the reaction force, I cannot put more force on the paper than the paper can put back on me. And if it's floating in the air, I can't put very much force on it because it can't push back very much. And so I can't put any more force on it than it can push back, because Newton's law can't be ignored, and I can only hit it as hard as it can hit me back. Now, if I were to hold it tight, then I can hit it and it will push back a little harder. I might even break the paper. Okay, if I put it in front of a brick wall, then it can push back a whole bunch, and I get bloody knuckles instead of tearing up the paper. But if you just have a floating piece of paper here, then you can't hit it very hard. Why? Because you can only hit it as hard as it can hit back. All right, and so that's basically because of Newton's first law. All right, now one of the other things we want to talk about is that the forces are equal to each other. The reaction force and the action force are the same, but the results of it are not the same. And we did this example outside with the bottle and the cork. When the pressure inside the bottle builds up, okay, it eventually shoots the bottle off one way. I had to hold it to make it let go, so it didn't work so good. And it will shoot the cork off the other direction, okay? But which has more mass? Well, the bottle with water in it has more mass, so it doesn't go very far, and the cork goes really far. Why? Well, it has to do with acceleration formula, which we learned, okay? And basically what we're saying is, if we have the bottle, well, let's say we have both of the bottle and the cork, okay, so we're going to have bottle and the cork are going to have the same force acted on it. So let's just put a little F here for force. Okay, they have a force. It's pretty good, but okay. But let's say that the bottle weighs 5 times as much. It has a lots of mass. I hope you can see that. Not showing very good. It's not that very good. Okay, but the cork has a relatively small mass. Okay, well, if you take the same force divided by a big mass, you're not going to get much acceleration, so it's not going to go very fast. Okay, if you get the cork, which has the same force but on a smaller mass, it's going to go a lot faster and accelerate. Okay, and so even though the forces may be the same, if the masses of the two objects are not the same, then you're not going to have the result. Just like when I kick that bowling ball, if my foot doesn't have as much mass as the bowling ball, so it may do more damage to my foot or have a bigger effect, deceleration on my foot, than it does actually accelerate the bowling ball very much. All right. One more experiment. It'll take me a little while to get going, but we'll get it together and then we will probably be done. This is a trough, if you will. It's actually a big PVC pipe cut in half, and it has a little cradle looking thing here. All right, and we have a little thing here we're going to hook up on the ceiling, so I'll do that and then we'll get to the next step. All right, for the next step, we have some hydrochloric acid here, and that's not actually going to run our reaction, but we're going to use that to produce a fuel. We need hydrogen. And we're going to pour acid into water. That's how that is recommended. All right, then we're going to take zinc, which will react with the hydrogen chloride, which is hydrochloric acid. Same stuff that's in your stomach, although not exactly in the same circumstances. Okay, so don't be panicky that, oh no, my stomach's going to eat holes in me. Okay, we're going to drop it in there. See how much of a reaction we get. All right, we're going to let it kind of push the air out of there for a little bit. And then we're going to put a balloon over it and try to capture this gas. Never know exactly how much to put on, so it's always kind of a guessing game. Well, not that much apparently. Okay, try again. Alright, there we go. Try it again. Maybe this one's gonna work better. We will see. Alright, we will collect this and we'll come back to you once we get done. Alright, we have collected our hydrogen gas now. We're going to put it inside this Coke can and this Coke can. Now we used to try to put some kind of fuse in there, but we found that it's better to light it directly with a match. Okay, so now we're ready to load it into the cradle. All right, so here we are. We've got our cradle up here. Let me put this up there. Boom, set it right there. All right. We have a match tied onto the stick here, so I don't have to get too close to it. When I light it, light the match, and then we will light the hydrogen and see what happens. Oops, there we go. All right, we're gonna light it. All right, boom, there we go. All right, we get a boom, and that's always good. All right, so once again, you'll notice that we had gas exploding. All right, it put a force on both ends, and you'll notice they roughly went about the same way. I don't know if you can see on there, of course, but let's see if we can do it here. This one. A little bit past the table over here. This one. A little bit past the table over there. All right.